Over to you, sir.
Thank you. Thanks for wonderful introduction. So let me know if I'm visible to you all.
Yes, sir, you are visible, sir.
Okay, thank you. So quickly, let me share my screen.
నిన్ను కాదు
My screen is visible to you?
Yes, sir.
Okay, fine. So a very good morning to all of you and welcome to this session. This is Dr. 𝐂𝐥𝐮𝐝 and I'm working as a senior R&D engineer at Alstom. So basically, our company Alstom provides metro solutions. So most of the metro solutions you see globally is provided by Alstom. So this is the agenda for today. We will see what is a critical system, what is a safety critical system, and then how can we ensure the safety of these critical systems. So as most of the part is already covered by your colleague, my introduction part. So yes, I'm working as a senior R&D engineer at Alstom, and I did my PhD from MNIT Allahabad, MTech from IIT Kharagpur, and BTech from BPUT, Biju Patnaik, all in computer science only. So coming to the formal methods, so I don't know like how many of you are familiar with this word formal methods, but this is a buzzword in industry nowadays. So I believe most of you, once you will complete your graduation, you will be going to industry. So that's what I thought, like it's better to discuss a recent trend. It's not basically recent, but it's very important trend in industries nowadays. So let's say if I talk about any of the safety critical systems, for example, first of all, we'll try to understand what a safety critical system is. So any software system which involves human lives, that is known as safety critical systems. Or let's say any software which involves huge financial uh, impact, those softwares are known as safety critical systems. For example, let's say if I talk about autopilot, right? So in avionics, whenever you are flying in the aeroplane, so this is controlled by a software called autopilot. So can we even expect 0.0001% of flaw in that system? No, we cannot expect minimum or minimal flaw also in that system. Why? Because it's a safety critical system and it involves human lives. So there are many other applications also, like you can go for the medical instruments or medical equipments, then our defense systems, our avionics, metro solutions. So nowadays we are working on a project like which will be giving you a driverless metro projects, driverless metro solutions. So there will not be any driver involved in those metro solutions. So these softwares or these systems need to be verified, need to be tested thoroughly. So do we really think, or do you really think that software testing, whatever testing techniques we are using in our industry, or let's say in our college days, so these testing techniques are enough to say that fine, these softwares are tested thoroughly, these softwares are verified thoroughly, and then it can go into the business? So before coming to anything, I just wanted to show you this slide to understand in a better way that what is the difference between software testing and formal verification or formal methods. So for example, let's say this is a graph, or you can say a tree. This is a tree or graph, whatever you say. So in this graph, actually what we can see is, let's say if this is a graph represents a program or a software, and then if you will go for the testing of it. So as we all know that software testing, what it means we are supposed to create some test cases or test scenarios or test suits, right? So let's say if a program has multiple branches, and then if you have created, let's say, one test suite that is, let's say, D here, and this test suite can go in only one branch of this execution, one branch of the program. And then if you will get the correct result, yeah, you are very happy that, okay, fine, my software is working fine. But what about these other branches, right? So we don't have any idea even that whether we have covered all the other branches or not. Let's say if it is a simple program, we can actually have an idea. For example, if you write a program in which, let's say, there are if-else statement or for loop is there or while loop is there, and then if there is a countable number of loops or countable number of control statements, then actually we can design some test cases so that it can go in all the branches of the program. But what about if the program is very huge? It's a very complex program. Let's say 10,000 or let's say, millions of codes are there in a program, in a software. Then really it will not be possible for us manually to write or to design test suits or test cases so that we can cover the entire path or the entire branch of the program. And let's say if you have missed one particular branch, let's say you have designed enormous number of test cases and test suits, but let's say if you have missed one particular path to test that how this path will behave, and let's say at the real time when you will deploy this software at the real time, if this particular path will have some issue, will have some error, then your entire system is going to crash, right? So you have to be very sure that the system which is involved in our human lives, these systems are tested thoroughly or not, or whether it is verified thoroughly or not. So that is why this formal methods came. So formal methods will, what it will do basically, it will go through each and every path of the program and will tell you that in this particular path, for this particular input, there is an error. So before deploying the software, you can actually imply or you can actually know about this error. So there is a basic difference between software testing and model checking or any formal method techniques are that software testing can tell you about the presence of errors, but it will never tell you about the absence of errors. Whereas formal methods can tell you about the absence of errors too, that to be in advanced, right? So it was just to give you a glance of formal method that how actually this formal method works. But once again, coming to the basics, like formal method is not a set of tools so that you can directly give input a program and then you can check that whether all the paths are covered or not. So basically, formal methods is a set of mathematically based techniques and tools to specify, develop, or to verify a software system. So if you want to become a formal method engineer or a formal verification engineer, you have to be very good in mathematics and you have to be, your fundamentals have to be clear in mathematics. Then only you can be a good formal method engineer. And then so basically what we do is like, how can we say, like how can these formal methods work? So basically there are 3 steps. First of all, let's say I have one system which I need to verify formally. So what we can do is, first step is to model that system. We can actually model that system. And to model that system, we need a language typically known as a description language. I'm going to show you like how these languages looks and what are these languages, where can we find these languages. So basically, first of all, you have to come up with a model. And whenever I say model, it doesn't mean that a graphical kind of model. So it means that you have to write a code to get that model. And once, let's say you have a model with you, then the main important part is what you are trying to verify in that particular system. So these things are known as the properties to be verified. For example, if I take the example of autopilot, so what you want to verify actually? That once the plane takes off, then the entire system or the entire aircraft is getting controlled by an autopilot system. So there are many properties like if latitude is this, if longitude is this, or let's say if the wind direction is this, then what or how my system is going to behave. Like so, these are the properties which I need to check in that particular model, and these properties also you have to write in some different language, and then there should be a framework, there should be a mechanism in which I can pass this model as well as I can pass these properties, and then this framework can tell us whether these properties are satisfied on this particular model or not. So basically these three steps are involved. First is to develop the model. Second is to identify all the properties you need to verify on that particular model. And the third is you need a framework where you can give this model as well as the properties to be tested or to be verified against that model. So there are many other, like there are other different techniques of formal verification. The common one is known as model checking. So I was talking about model checking. So basically, model checking, what it will do, that it will exhaustively explores all the parts of that particular model, and it is going to tell you that in which particular path, for which particular input there can be an error. And there are, as I said, that if you want to convert your properties into, a logical formula, there is a language. There are many languages, but these languages are known as temporal logic. So everything you have to convert it in the form of logic only. We are going to see it later. And then other popular technique is theorem proving. So this theorem proving is, let's say, if you have, how you have proved your theorems in your mathematics, the same way we have to prove these properties over a system. For example, if I ask you like, what is the value of 2 plus 2? Immediately you are going to say 4. But if I say you like, how you came to know that 2 plus 2 is 4? So there are basically two theorems that we know, and the theorem is like predecessor and successor, right? So what is the meaning of successor is that if I add 1 to any number, it is going to give me the next number. And predecessor means if I subtract 1 to any number, it is going to give the number 1 which is behind to it. So I know, like we know these two basic theorems or basic fundamental concepts, which is also known as lemma or axioms. In mathematics, you must have heard these terms. So by knowing only these two lemmas, we can actually, calculate the sum of any two numbers, right? So this is how this theorem proving work, that you have to come up with all the fundamental formulas, all the fundamental lemmas and axioms, and then based upon these fundamental lemmas and axioms, you can actually verify a bigger or a complex formula or a complex theorem. This is what known as theorem proving. And again, whatever I talked, these all things has to be done with the coding itself. There is no mathematical framework so that we can write equations. We have to write everything in the form of code itself. Fine. And you also might have understood like what is the code coverage in your college days, especially in software engineering courses, if you had have gone through that. So basically, if you have written a program, then if you have tested, then you are, let's say, if I have written a program to add two numbers. So what basically you do as a college student is like whenever you execute that program, always you give two numbers like 5, 10, 25, 30, or let's say, if you are a good programmer, you can give some floating point number also 5.1, and 10.5. But let's say, what if it is, let's say, if I give some A and B as an input, if I give A and B. So many times, many students, they doesn't go for validation. Like if user will give some wrong input, then how my program should behave. Let's say intentionally or by mistake, if I give two strings to your program, then how your program behave, whether it got crashed or it will tell me, a message that no, it's not a valid input. You must give two numbers or two floating point numbers. And also, let's say if there are many if and else, for loop and while loop, all the control statements are there, then what is the coverage of that particular code? Coverage says that whatever test cases you have designed, whether it has covered all the statements of the program or not, whether it covers all the decisions, all the branches of the program or not, and what about the functions, whatever functions you have written in your program, whether it has covered all the functions of the program or not. So now onwards, whenever you try to write a program, just keep one thing in mind, that whenever you are designing a program, you design a program or you write a program as a programmer, but whenever you are giving some input to test your program, whether it is working fine or not, at that time you become a validation engineer. You don't be a developer at that time. You just try to give inputs, in such a way that you try to crash your program. You don't try to pass your program. You try to crash your program, that what input I should give to my program so that my program will get crashed. Okay. And then if you can cover all those situations as a developer, then your program will be a very fine program. And that is how the industries also works, right? So let's say if you have to implement one particular module, we are not only concentrating on that particular module to develop. Rather than that, apart from that, we are also developing many things which will, protect our system, which will protect our software to be crashed, right? So these things also you should keep in your mind when writing a program. Already I explained this slide. So where can these formal methods can be used? So I believe you all know about the software development life cycle of a program, like what are the different phases of software, requirement definition or requirement gathering, then next comes to requirement specification, and then you must go for like design and then implementation and then deployment. This is how you are approaching in SDLC. But let's say many times what happens is that whenever you are trying to, gather the requirement, let's say if I want to develop a project or a software, so when you are going to collect the requirement from the customer, so what customer says you and what you have understood, there could be a difference between them. And then finally, once you have written all the requirements and then you give these requirements to the developer, that fine, these are the requirements you need to develop. There also, there will be some gap between you and the developer, like what you were trying to explain and what he understood or she understood as a developer. That also there is a difference between, there could be a difference between them. So finally, once you will, after some time, you will come up with a system which will be not as per the customer, because there were so many gaps in the requirements. Also, there were, requirements are sometimes ambiguous. It is not very clear, like what to do, what not to do. So if you will use these formal methods at the time of writing requirements only, then all your requirements will become unambiguous, right? It will not be ambiguous anymore. And once a requirement is non-ambiguous, then it will give the clear message to everyone, to developer, to validation people, to customer, to deployment engineer, everyone it will give a clear message. It will not have different meanings, right? For example, if you will write a formula in mathematics, a plus b whole square, so for everyone it is the same, a plus b whole square, right? But let's say if the same thing, if you will write it in a plain English language, the meaning of these English languages can be different from other people, right? Because of their basic understanding of English, or because of the person who has written that requirement in the plain English language. So this is also a very good idea to apply these formal method techniques at the time of requirement only. And of course, if let's say you have not, so if you have used this formal method at the time of requirement, so So you can see the differences between them. So if you will not use formal specification, then it may happen that in specification you may take less time, but in design you will take more time. In validation, in fact, you need much more time. But if you will use formal specification, then it may happen that it may take some more time at the time of writing specification, but certainly for designing and for validation, it will take very less time. And also one more thing, if you will notice here that you won't have any rework in case of formal specification. But if your requirements are ambiguous, then it's possible that after some time or at the design level or at the validation level, you will have to come back to the specification part as a rework, right? Because of your requirements were not very clear. So it's very good, or it's always good to have, application of formal method at the time of formal at the time of requirement specification, especially in case of safety critical systems. And but the question is like, if this method is so powerful, then why it is not very popular among industry? Like why all industries are not using this formal methods? The answer is very straight, simple, that it is expensive, right? So how it is expensive? Like, because it needs a lot of mathematical trainings, it needs a lot of hard work to be performed. So it's very typical and it's very expensive. That is why many industries don't use these techniques in their software, right? But definitely the industries who are responsible to develop safety critical systems, they use these formal methods in their software development life cycle. So I have taken one example of safety critical system here, that is separation kernel, and we will see some real examples of it, and we will see some real properties that how it could be verified. So what the separation kernel is, like, it is a kind of operating system only, but it's a microkernel. It's not a monolithic kernel. So there are two types of operating systems, or there are two types of kernels, you can say, microkernel and monolithic kernel. So whatever system or whatever OS we are going to use or we are using in our day-to-day life, that is known as monolithic kernel. And microkernels are specialized kernels or specialized operating system which has been designed for some specific applications, right? For example, let's say if I have to design or define one operating system for defense applications, then it will be different from the regular operating system what we use in our daily basis. So I have taken an example of separation kernel, which is in a specialized microkernel. Uh, so just these are the basics. I believe you know these things, like what are the kernel of operating system. So basically, kernel is something which can be interface between your applications and on your computer programs like CPU, memory, devices, right? And also it is known as a core of an operating system. And then processes, if any user process is there, it has to make a request for kernel through a system call only. So any process cannot directly interact with these resources. It has to go through some system calls through kernel. So as I said, there are two types of kernels, microkernel and monolithic kernel. So the basic difference between these two is, if you can see in this picture, that in monolithic kernel, everything is kept in the kernel space only. So basically there are two space, kernel space and user space. So in case of monolithic kernel, all the programs are kept in the kernel space, whereas in microkernel, only few programs like basic IPC or virtual memory kind of thing or scheduling will be placed in kernel space. Other applications are placed in the user space. So we can clearly see that, like, microkernels are more secure than monolithic kernel. Okay, but why it is more secure? Because you see that user applications are different, or it is placed separate from this kernel space. So users are not allowed to directly enter into this particular area. Whereas in monolithic kernel, users have access of everything. So it is less secure, whereas microkernels are more secure. But if I talk about the execution time, monolithic kernel will be fast. It will be very faster. Why? Because there will not be any switching between user space to kernel space. Everything is kept in one particular space. So execution will be fast here, whereas here the execution time will be more because it has to go for lots of validation process, and then switching will also be there, right? So this is the basic idea of microkernel and monolithic kernel. So monolithic kernels are basically huge in size, what we use in our daily life, and then these are weak foundations for building secure system. So we cannot really build a secure system with the help of monolithic kernel. Okay, there could be some attacks also on our monolithic kernels. What is the need of separation kernel? So I already said that if you have to go for a safety critical systems like defense and aerospace applications, then it is highly recommended that you go for a separation kernel or you go for a microkernel. And so there are many separation kernels. If you can Google it out, and if you want to know more about it, like what is a separation kernel and what separation kernels are used for which applications, you can basically go through it. But what I will try to do is, this is a basic architecture of separation kernel. You can see here that it's also known as a hypervisor. So directly, this is your core of the hardware, that means CPU, and directly on this CPU, it can be mounted. Your separation kernel can be mounted on the CPU itself, which has all the functionality which an operating system has. And then you can see in the above layer, there are many applications. And also we have restricted that which particular application can interact to which particular application. It's not like any application can interact with any other applications. No. So, for example, here application 1 is allowed to interact with application 2, but vice versa is not true. Application 2 is not allowed to interact with application 1, right? So these restrictions can also be there. And in separation kernel, there is a term called policy file. So basically, what we can do is, like, we can write a policy file. For example, in a general operating system, if you have n number of programs to execute, then you don't have basically control that which program will be executed first and then which program will be executed next. It will be the job of operating system only. Operating system will decide the scheduling of your all the programs. Or let's say you will not be able to decide that which particular program is going to store at which location in the memory, right? So this is all are very internal, and operating system used to take care of these things. But in separation kernel, if I have n number of applications, then actually I can decide that which particular application can reside in which particular partition of the memory. And then also I can schedule our programs, like which program will be scheduled first and then which can be scheduled next. So actually we can have a control on our operating system or on our microkernel. This is how it differentiates between monolithic and microkernel. So basically, in general operating system or in monolithic operating system, you might have heard something about process, and here we term it as subject, right? So basically, both are same thing only. There also process means a program which is under execution. Here also the subject means same. There also you have process state, process specifications. Here also we have subject specification and subject state, and there could be many states, like whether it is in CPU registers, or what is the instruction pointer, what is the stack pointer of a particular subject. And there also you would have seen something PCB, process control block. But here in case of microkernel, we see it as a VMCS, that is virtual machine control structure, which will store all the information of a subject. There could be two types of subjects. One is naive, another is virtual machine subject. Naive subjects are the subjects which can directly execute on the core of the system or on the hardware of the system. You don't need any host operating system for that. But in virtual machine subjects, you need a host operating system. So if you have gone through the VMware, So how this VMware works is like there will be an operating system in your system, in your computer, and then in that operating system you are installing VMware. For example, your Windows are installed, and then if you are installing VMware to use Linux or something, so that is an example of virtual machine subject, right? Because you need a host operating system to execute that particular program. So this is how it looks like, VM and naive subjects. And there are other processors also. So Intel VTX properly, precisely this Intel VTX processor nowadays, it supports this VM and non-VM mode. So there will be a command called 𝐸𝐸𝐿. So if you will give this command 𝐸𝐸𝐿, you will enter into an area called VMM, virtual machine monitor, and then if you will give the command vmentry, then you can actually go to a non-root mode, and you can actually execute a virtual machine applications. Once again, if you are done with virtual machine applications, you can give vmexit command, and you can come to a VMM. And if you want to come out from this VMM, you can give simply 𝐸𝐸𝐿 command, and then you can come out of it. So these operations are available in Intel VTX processor. And as I said, there will be a policy file. So in this policy file, actually, we can write everything, like how many processes we have, how many subjects we have, which subject is going to reside where, and which subject will be executing first, and then which subject will execute next. So all these informations you can actually write in a policy file in your before deploying this system. I can say that it's very static in nature, but in case of monolithic operating system, you don't have control over this. But here I can actually come up with a policy file which can be the collection of all these informations, and then finally we can mount this policy file on a system, right? So that it will become a microkernel. It is I have taken an example of Mune separation kernel. It is known as Mune. It has been developed in Switzerland in some university, and like in my PhD work also, I verified some of the properties of this. So basically, if you will see that this is a Mune tool chain, so all these policy files will be there, and then by using these policy files, I have built this Mune separation kernel on the hardware of the system, and then I can have many subjects, and then finally I can have a control over the subjects, just to deploy a safety critical system. So yeah, so what is the need of formal verification? So if you have developed one safety critical system or software, directly you cannot go and use it into the business. Directly you cannot use those softwares. For that you have to go for some certifications. So if you will verify all your requirements, functional specification, high level design, everything, you know it everything, if you will specify formally, then it will be, you will get a certification, EAL7 certification. It means your system is fully formally verified. If you have verified only requirement, let's say, you will get EAL5 certifications. So if you will get EAL7, that means your software is fully formally verified, and then it can go for any safety critical applications. There are many certifying agencies like CC, SPKK. There are many certifying agencies also. So now we will look one particular property of this Mune separation kernel. The property name is data separation. What this data separation tells us, data separation in separation kernel ensures that the subjects or applications belonging to the different security domain adequately executes in their predefined partitions in isolation from each other as per the system policy file. So for example, let's say if you have many applications to execute, then you can actually be sure that if I have given, let's say, partition number 1 for subject 1, partition number 2 for subject 2, in the policy file, if I have written like this, so whether it is really working as per my policy file or not, Or is there any flaw that, my one application, even if it is not allowed to reside in partition 2, if it is getting resided into partition 2? So these properties actually I need to verify on the mule separation kernel, that whether these properties are getting satisfied or not. So this is how our memory looks like. And if you will see, this is the like working principle of data separation. What I said, that you will have mule separation kernel, and then if any subject is there, then what it will do is it will take the base register of the particular subject, and it will check the limit register. So it will add the limit into it, and then it will check that this particular subject is allowed to access this location or not. So let's say if this is allowed to access this location, then fine. And if not, then there will be a trap handler, or there will be a kind of an error message that no, this subject is not allowed to execute or not allowed to access this particular memory location. This is how this model looks like, although it's very simple model, and I have taken only two subjects over here. It's a very simple model, but you can see the complexity. In two subjects only, we have around 20 number of states. So if, let's say, you have kernel active, then you can go to some state, whether S1 is ready, S2 is ready. So you can go into it details. I'll share the slides later on. And just I wanted to give you a kind of feel that in two only subjects, like we have many number of states. This is known as the actual model or the abstract model of our code. And then you have to list out some of the security requirements. So what are the properties we needed to verify? We needed to verify no exfiltration, no infiltration. What it means, that data processing in current partition should not affect the data of other partitions. Also, data processing in any other partitions should not affect the current partition. That's what we need to verify, right? These two properties needs to verify. And in order to prove these two properties, we have many other sub properties. For example, each partition must be isolated from other partitions. The space of kernel must not be accessible by the user process. So you have to identify, and then you can see that all these properties, what I need to perform, verify. So all these, properties are written in a formal language. So this is something, it may not be very familiar to you, but I am very sure that you would have seen these terms in mathematics, like E stands for existential quantifier, there exists, F stands for eventually there will exist something, right? A stands for all in mathematics. So for all branch, eventually means in future, sometimes this will happen, that the value of S1 will become 5 and value of S2 will become 5. So this is how we write all the properties and the model separately. And then finally, we are going to execute these properties on the model. And then it will tell you that whether these properties are true or false under the model. This is how this formal verification works. So I hope I gave you a good glance of formal methods. And last, we came to a conclusion that we have seen a mule separation kernel, which has been chosen for its formal verification. And like I have covered only one property, that is data separation over here, due to the limitation of time. There could be other properties also, like information flow security, so that we can restrict all the processes, that you are not allowed to interact with other processes, or are you allowed or not. Temporal separation, which means we can schedule our processes or subjects in the system. So there could be many more things which can be done with the help of formal methods. These were the references. Yeah, thanks. If you have any questions, I'm open for that. That's all from my side. Yeah. Any questions? Am I audible?
Yes, no doubt.
Yes.
Okay. Okay. So fine. This is all about formal verifications and formal methods. So I really believe that you all are like third year or fourth year students of your undergraduate of your engineering. So it's a very good opportunity for you all before going to industry, that if you can have some skills of formal methods, because it is something very unique and very niche skill. And if you can have some knowledge of it and some basic understandings of formal methods also before going to industries, so you will be having definitely you will have a unique place in the industry, that is for sure. And yeah, so if there if let's say if any of you want any other help, or let's say any further help in this particular topic, please feel free to ping me. Also like in our company, like we are hiring many interns for different domains. So if any of you would be interesting, you can go and apply, and we will see if your profile gets shortlisted. We can contact you, or we can offer you some interns also. And it's a really very niche skill. Very few people are there in the industry who are really involved in these formal method applications. But believe me, if you have this formal method or formal verification background or knowledge, there are plenty of opportunities in the industries, and you will be also different from others, because it needs not only the coding, it needs not only the computer science knowledge, also it requires your mathematical ability. And I'm very much sure, like as you all are engineering graduates, so you all will be you all are good in mathematics. So just you have to use your mathematical skills and to learn formal methods. That's all from my side. So if you have any questions, we can take it. If not, then we can close this session. Yeah. Okay. So can we close this session now?
Yeah, sir. Thank you so much. The beautiful thing about learning is that no one can take it from you. So never give up and keep learning. On behalf of the entire NGC Club and VIP, I would like to thank our honorable speaker. Thank you for inspiring and encouraging us with your words on this special day. Special thanks to our club faculty coordinator Ganesh Reddy sir, and thanks to Santosh sir for supporting us on every event and webinar. And last but not the least, I would like to extend my gratitude to our audience for coming and making this webinar a successful one. Thank you.
Thank you. All the best. Bye-bye. See you all.
Sir, just a second. I would request everyone to turn on their videos for a picture.
Okay, I think I have pressed this leave button, so it's okay if you can. So I'll keep pressing it. Yeah.
Yeah, sir.